afternoon, good evening. Thank you so much for joining us today. I am Melissa Mendes. I'm introducing our speaker today, Cédric Jockel. He has done his undergraduate and master's study at Goethe University in Frankfurt, Germany. Since September 2023, he's a PhD at Max Planck Institute for Gravitational Physics in Potsdam, Germany. His research interests lie in compact objects of different types, how to model them analytically, numerically, and how to extract quantitative signals that can be observed. His master's project, he investigated neutron stars with an added classical microscopic scalar field, representing a type of ultralight bosonic dark matter. Apart from stability and mass-radius relations of these objects, he studied the tidal deformability and constrained the dark matter particle mass and self-interaction strength. So for his PhD project, he's studying supermassive stars, possible progenitors of supermassive black holes found in the early universe. Some observed black holes are too massive to have grown using regular accretion in the time available in the young universe, so a possibility is that the progenitors of supermassive black holes started at higher masses, potentially with supermassive stars that grow to 10 to the 5, 10 to the 6 solar masses for rapid accretion. I'm sure we're going to hear all about this in his talk today. Yes, Cédric, the stage is yours. Please feel free to ask questions at the end, and we'll be here to help you with that. Thank you.
Yes, thank you so much, Melissa, for the very nice introduction. And also thank you very much to everyone and to Irina for inviting me and giving me the chance to talk to you about some really interesting piece of science. So let's say I'll just share my screen real quick. And today I have something to talk to you, right? I want to talk about the scalar and vector dark matter admixed in neutron stars. So what is the basic idea? Is, let's say we have some neutron star and we also know that dark matter exists in some shape or form. And the idea in this project is that maybe the dark matter could somehow end up inside of the neutron star, and then the additional dark matter would then change the properties of the neutron star, for example, the radius or the total mass, or also the tidal properties in form of the tidal deformability, for example. And the work I'm presenting is summarized basically in those two papers you see here. So if you're interested, you can have a look. All right. So we have dark matter and we have neutron stars, and I'll just do a little bit of introduction, a bit of prelude, so to say, by starting just what are even neutron stars, right? Just a little recap. As far as we know, neutron stars are those highly compact, dense remnants of heavy stars which have gone supernova. And then they leave behind some quite small star, which is around 10 to 15 kilometers, depending on the model, with very high densities. This, of course, those really high densities makes neutron stars very interesting for the research of the nuclear matter equation of state. And using those neutron stars, maybe we will be able to find out how matter behaves at very high densities. Right, but in this neutron star, in this work, we'll do a little spin on the topic of neutron stars, because we will use neutron stars to try to probe the properties of dark matter instead. Right, so in neutron stars, you have those mass-radius relations, which are quite famous. And if you add dark matter, those relations might change, which is exactly what we'll be studying here. So neutron stars, what is the next ingredient? It's dark matter. So dark matter is really this elusive object, elusive substance that we do not really know a lot about. Basically, the only thing which is known is that it is invisible through light, so it doesn't interact with photons basically at all, right? That's why it's dark. It has some gravitational effect on its surroundings. We see this, for example, through the rotation curves of galaxies, right? Through cosmological simulations and cosmological evolution, we know that dark matter is quite abundant also. There's just a lot more dark matter around than baryonic visible matter. So we also know it's slow moving, so it's not fast like neutrinos flying around everywhere, but dark matter coalesces into some macroscopic structures. Also, it is weakly interacting at most weakly interacting with the standard model. And that's precisely why we haven't been able to detect it yet, right? And of course, something such unknown as dark matter sparks a lot of interest in different models and different attempts to explain what it exactly is. You can see a recap here in this image. There's really everything from, or maybe dark matter is made out of some new particles that we don't know, or maybe it's some modification of the standard model in some way, or maybe it's not a particle at all, it's some macroscopic object, or maybe dark matter is not even an actual thing, but it's just our theory of gravity works differently on different scales, right? So you can get the full bandwidth of ideas here. But in our case, dark matter is a type of particle and a type of light particle. And those light particles have quite interesting properties, which I'm going to talk about in just a minute. So this brings us to the question, how do we, in our case, understand dark matter in this work, at least that we did? In our case, we say that dark matter is some kind of gravitationally interacting bosonic particle. And there's really two ways of looking at particles, as you all know. You can view a particle as some kind of point particle, right? It's essentially a small sphere flying around, for example, in a gas or some cloud. Or you can also treat a particle as a wave. And then it becomes important, what is the relevant scale you're looking at, right? If you look at subatomic scales, then the correlation length, the wavelength of the particle, the Compton wavelength is comparable to the system that you're interested in. And then you need to treat it as a wave. But on macroscopic scales, to study the Earth's atmosphere, for example, the small wave properties of the molecules usually will not be relevant. But what happens now if we have some kind of particle which has certain properties, as though it has wave properties on astrophysical scales? And this is the realm of ultralight particles, which is exactly how we will model dark matter in a way. So if we put both together, we get a so-called fermion boson star, because we have a bosonic dark matter, and we have the neutron star, which is made out of fermions mostly. And you can think of it really in those two ways. Either you have some neutron star, which is in the center, and then around you have a cloud or an accumulation of dark matter, which just is gravitationally bound somehow to the neutron star. Or maybe the dark matter accumulates inside of the neutron star, and then it just becomes a sort of core of dark matter, right? And which of those two cases is relevant depends on many factors, right? First, it depends on how much dark matter do you even have inside a neutron star, right? If you have a lot, it's more likely then that you will have a cloud. And if you don't have a lot of dark matter, it's more likely then that you will just have a little bit concentrated in the center. And also depends on what is the actual scale. So what is the correlation scale, the correlation wavelength of your dark matter particle, of the macroscopic wave, right? And if this wavelength is very large, larger than a neutron star, then you might have some kind of dark matter distribution around the neutron star as a cloud. And so you might ask, how does dark matter even go into neutron star, right? How does it end up there? For example, dark matter could accrete. Just through time, you have gravitational interactions of some dark matter particles with surrounding medium, and then it slows down. It will slowly accrete in the neutron star and just accumulate. Or you could have the other way around, actually, that the dark matter was there first, and then the baryonic matter will just fall into the gravitational well of the dark matter. And then you have also the same effect in the end. If you want to go a little bit more exotic, you could have mergers of neutron stars and boson stars. So boson stars are just the pure scalar field, a pure dark matter self-gravitating object that you could have. Or you could also have some kind of interaction of dark matter and the standard model, that you could maybe have some standard model particles that decay into dark matter particles. And then those would naturally coalesce inside of a neutron star and build up over time. So our objective now, what do we want to do? We want to find a way to describe neutron stars, but also include dark matter. And then we want to use this information to learn more about the properties of dark matter. So what we'll do now is we take a regular neutron star and then add an additional gravitationally bound bosonic field. So bosonic field, what I mean by this is you could either have a scalar field, or you could also have a vector field, which is both cases that we studied. And then we say, yeah, okay, this scalar or vector field acts as a kind of Bose-Einstein condensate. So you could really think of the neutron star, and inside or around the neutron star, there's some condensated dark matter field. And what kind of field you actually have, or what are the properties, depend on the Compton wavelength, right, which is written here. And the important proportionality here is this 1/m. So small m is the mass of your dark matter particle. And you can see if you make the particle mass smaller and smaller and smaller, then your correlation length becomes larger and larger and larger. And precisely at the point where you start to get condensates which are on the same size scales as neutron stars, then you end up with masses of around 10 to the -10 electron volts. This is very small. This is an ultralight particle, right? Which is, of course, not measured until now, but yeah, it could happen. Just as a comparison for you, if you look at bosons on the scale of the quantum chromodynamics, right? The lightest one is the pion, and it has a correlation length of roughly 9 femtometers. So we're looking at many orders of magnitudes smaller in mass to get many orders in magnitude more in correlation length. And of course, this kind of mass is not in the standard model right now, but there's some contenders. For example, the QCD axion has been proposed various times, or you could have some different kind of ultralight particles. And those are generally called wave dark matter because exactly they do exhibit this macroscopic wave behavior. Right now I get to a little bit of mathematics, but I try to be not too long about this. So what are we actually doing mathematically? Mathematically, a neutron star with dark matter, also those fermion boson stars, right? They can be modeled using a gravitational part coupled minimally to a scalar field. So minimally coupling means that the dark matter or the scalar field, or also vector field, right? They only interact gravitationally with gravity and with the remaining neutron star matter. So you have this action which has curvature in there. Then you have terms regarding the scalar field with some potential. And then you have a matter term which describes the neutron star, the neutron matter, right? The neutron star matter of your fermion boson star. You can use this action to derive equations of motion, which are exactly the Einstein equations. But now your energy momentum tensor is made up of two parts. So one describes the neutron star, and the other one will describe the scalar field or the dark matter content. And in our case, we say, okay, yeah, our energy momentum tensor for the neutron star is a perfect fluid. And the energy momentum tensor of the scalar field is given by this. You will get this if you do the variation calculation. And this equation 4 just describes your energy and momentum content of your scalar field. So if you take all of this together, you can make some ansatz for the scalar field, for the space-time metric, and then you can derive equations of motion which describe this combined system of neutron star and scalar field. Then you get equations which look like this, right? You should maybe write them down because it's very important. Yeah, but essentially, so we have a system of coupled ordinary differential equations. And this system is then closed by an equation of state, which describes the neutron star matter. right? It's just a relationship between pressure and energy density and other quantities. Also temperature and chemical potential all go into the equational state, and it encodes your microphysical properties of your neutron star matter. And then for the scalar field part, or for the bosonic part, you can choose some potential. In this case, we will choose a self-interaction potential. So you have a mass term with the m squared, it's the mass of the boson. And then you have some self-interaction term with the lambda and then phi to the 4. But this specific shape is quite interesting for people who know particle physics, right? Because it's the standard case of a self-interacting boson. All right. Now what can we actually do with this? It is possible to integrate this equation numerically, and then you can get radial distributions of matter and the scalar field. As you can see here, I have plotted radius versus the field amplitude and the pressure of, so the pressure of the neutron star matter and then the field amplitude, two different quantities. So the orange one is the neutron star matter, just the pressure as a function of radius. And those dark blue lines, or violet, I guess. Yeah, those are just a scalar field as a function of radius. What you can see, interestingly, the continuous line is the neutron star without any dark matter, just pure standard neutron star, no dark matter added. But now if you increase the amount of dark matter, you get to the dashed line. And now somehow your matter is more compressed because you stop at a smaller radius. And if you add even more of the scalar field, then your radius terminates at even smaller rate. Your pressure terminates at smaller radii. And this means that your whole neutron star has a smaller radius than it had before. That means that this added scalar field that makes your whole neutron star more compact and leads to a smaller radius, which kind of makes sense if you think about it, because you're adding additional energy, you're adding additional mass in the center of the neutron star, and this additional gravitational pull will then pull the neutron star more together, and this will make it more compact. Another case is also possible, depending on the mass of your particle. You could also have the scalar field spilling out or being geometrically larger than the neutron star. And then you could have a total system which is less compact actually than before. Right? This could be relevant, for example, if you're looking at some neutron stars in a binary system, right? Then you could have those dark matter clouds of two neutron stars, for example, interacting with each other. And then they could change the in-spiral dynamics of binary neutron stars, for example. So now we take this one neutron star that we have just calculated, this fermion boson star, right? And it has two properties that you can set. You can set the pressure in the center, or the density in the center, and the value of the scalar field in the center. If you do this, you can make a plot like this to the left. And each one of those little points is one configuration of those fermion boson stars. You can compute a grid out of this, and then you can do a stability analysis. You see this black line here is the stability curve, and this is a generalization of the stability analysis you can do with pure neutron stars. Right, you know, for neutron stars, you have this mass radius curve, which goes up, and then at some point it has a peak in the mass, and then everything to the left of this peak is unstable under radial perturbations. And when you do a similar analysis also for the fermion boson stars, then you get this curve. And this basically means that every configuration in the bottom left part of this plot will be stable if you perturb it. And everything which is on the outside will be unstable. And if you perturb it, it will either migrate into the stable region, or it might also collapse into a black hole, or it might also disperse and then just basically not exist at all anymore. You can do this using the stability criterion, but details, let's say, are not super important. If you're interested in this, you can also ask, and we can see. So what are we doing now? We're now interested in only the stable configurations. And we're also interested in how the amount of dark matter affects the radius and the mass of the total configurations. You can get something like this. So here I've just taken the same plot as before, and I've taken all the stable contributions, all the stable configurations in the left bottom part, and then put them into a mass radius diagram. And this will look something like this. And what you might notice immediately is that compared to the standard neutron star case, where you just have one line, which corresponds to one nuclear matter equational state, you now have a kind of region of possible configurations. And every star, every configuration which is here, has a different amount of dark matter inside of it, different dark matter fraction, basically. And now you just have this region of possible stable configurations, which is quite interesting. And now, if we have some observational constraints on the radius and the mass, then we might be able to constrain what exactly are the properties of the dark matter particle. Because this region that you see here will change depending on the properties of your dark matter particle. Right? If you have some different masses of the particle, or if you have some self-interaction, or depending on how strong is the self-interaction, then we might be able to constrain the dark matter properties. But there's a problem which is introduced here. As you can see, there's some points which cross each other. And what it means is that you could get the same mass and the same radius, but for different amounts of dark matter inside of your neutron star. This, of course, introduces some degeneracy in your solution. But yeah, that's just how it is. So the only way to fix this is to just get more and more different quantities that you can compare and then try to constrain. So here I've just plotted a bit more different configurations. I'm varying from left to right the strength of your self-interaction. So on the left is no self-interaction at all. On the right is a strong self-interaction. And on the bottom, I changed the mass of the scalar particle. So you can see which part of your mass radius curve is populated by your fermion boson star. By your fermion boson stars will change depending on your dark matter properties. And this is exactly how you might try to constrain your dark matter. What is also quite interesting is that I've marked here in gray the Buchdahl limit. The Buchdahl limit is this kind of most compact configuration that you might get of some self-gravitating object. And if it gets more compact, it will collapse into a black hole. And in this case, it looks like the fermion boson star is violating this Buchdahl limit. But actually, it is not. Because what I'm plotting here is the radius of the neutron star. That is precisely the point. It is the radius of the neutron star component. Right? The scalar field itself, or the bosonic field, might extend outside of this radius, but it will not be visible because it's dark matter, right? If you look through using electromagnetic radiation, we will not be able to see the dark matter, but we will be able to observe the surface of the neutron star. So this, you could think of it like this: you have a certain, like a neutron star with a certain radius, but then you have additional matter, additional mass because of the dark matter, and this might increase the observed mass of your combined system. And so if you find something like this, an object which is violating the Buchdahl limit, this could be a possible hint that there's something else going on than just a pure neutron star. Right, so if you other interesting things you can do with this, you can make a mass radius plot like this. So here I've just changed the mass of the particle and made it even smaller than before. So now it's in the range of 10 to the minus 11 electron volts and not 10 to the minus 10. And then you can get configurations which are actually higher in mass than just a pure neutron star can achieve. This is because of some scaling relations of the pure bosonic field configurations. They scale like 1 over the mass of your particle. So technically, you can even make arbitrarily large masses if you really wanted to. I think considerations like this are especially interesting if you think about this recent binary object which has been identified with some compact object possibly in the mass gap. So I'm not saying it is dark matter, probably it's not, but it could be one possibility to explain this unusual object. Right? And all of this is of course possible because we will only observe the neutron star part, the fermionic component of your fermion boson star, and not the bosonic component because the bosonic component is invisible. All right. Now, speaking of things that might be visible or not, we can go a bit further. So now we're interested in the tidal deformability of those fermion boson stars. And why is it so interesting? Essentially, the tidal deformability is a measure of how easy it is to deform an object. Usually, if you have some external gravitational field, you have a tidal field which then acts stronger on one side of the object and weaker on the other side of the object. And the tidal deformability is a way to quantify how easy it is to deform a neutron star, for example. What you do mathematically is you do perturbations on top of some fixed background, space-time background. Then you also do perturbations on top of the scalar field background. Then you can make some ansatz. Details are not so important. But essentially what this then leads to is a quantifiable measure of how the dark matter changes the tidal properties of the neutron star. This is highly relevant, for example, for the in-spiral of black holes or in-spiral of neutron star compact objects in general, right? And those in-spiraling signals will then be detected by gravitational wave detectors. And the templates which are used to model those in-spiral waveforms, they use the tidal deformability as one of those parameters. So there's some possibility that using some observed gravitational wave signal, we can constrain the tidal deformability, and using this observational constraint on the tidal deformability, we can then try to constrain the dark matter itself, right? Its properties, the mass, and the self-interaction strength. And so it is quite important for everything which has to do with coalescence of binary compact objects. So what you actually get when we run the numbers, when you do the calculation, you get something that looks like this. So this is the tidal deformability on the y-axis and the mass on the x-axis. And here you can see from left to right, I again increased the self-interaction strength. And on the bottom, the dark matter particle is just a different mass. It is larger by a factor of 10. And here you can see if you have different properties of the dark matter, the possible value of the tidal deformability can change drastically. Right? You can have 2 orders of magnitude difference just because you add a bit of dark matter. And actually, those results are quite sensible, even if you add a small amount of dark matter, which is very interesting. There's a general rule of thumb that you can have. So when you have dark matter, which is concentrated inside of the neutron star as a core, then generally this tends to decrease the radius of the neutron star. This tends to make the whole object more compact. And this makes it more difficult to be deformed by some external gravitational field. And the other way around, if you have a cloud of dark matter, because the radius of the whole configuration is larger, it will be easier to deform this whole structure. So if you, for example, find very, very high tidal deformabilities, this could be a potential sign that maybe we have some dark matter cluttered or coalesced around of the neutron star. Yeah. But what can also happen, of course, you can have different equations of state just for pure neutron star, which predicts different tidal deformabilities, different curves. And if they run through each other, then you might get the problem that you can reproduce the same exact results for one equation of state. using another equational state which has dark matter included. And yeah, this is really one thing about those degeneracies, that you have to be very careful when analyzing those results. And then, yeah, you can see maybe. So speaking of observations, of observational results, we can compare what do we predict and what have we measured so far. So those shaded regions over here are all current observational constraints that have been measured. And on the left, we see mass radius curves for different fermion boson stars with different amount of dark matter. So here the percentage is the percent of the rest mass of the whole object in dark matter. And as you can see, you can go both ways, basically. You can have some dark matter masses which decreases the maximum mass, the maximum stable mass of your neutron star, but you can also have some different dark matter mass which actually increases the total mass. And also the radius can be increased or decreased. But now what is very interesting, so if you look at this Hess measurement, right, which was a quite, let's say, anomalous or unusually light neutron star, which has been measured, this could, for example, be explained using some neutron star which has dark matter included. So what can happen now is you could have some equational state which does fulfill all the observational constraints except one, right? But then you add dark matter and it could be possible again to explain this different measurement. And if you look at tidal deformability, it's also quite interesting. So you can have different amounts of dark matter again. But now, what I personally find the most interesting part is this line with the 0.5% of dark matter. So here is only 0.5% of the star which is dark matter. And even though the tidal deformability changes drastically. And this could be very, very interesting for to try to probe dark matter, because this small amount of dark matter will usually not affect the radius or the total mass of the neutron star very much, but it can affect the tidal deformability by a great amount. So using combination of those different effects, it should be possible to constrain how much dark matter we may find in a neutron star. But of course, the error bars are still very large. And also the uncertainty in the nuclear matter equational state is also very large. So it might still be some time until we can definitively probe anything with high precision. So what is now? This is a very similar plot that you just showed you a second ago. But now it's for a vector field. So as I told you earlier, you can have a boson, dark matter boson particle, and we can describe it using a scalar field, which would then represent a spin 0 particle. Or we could also use a vector field, and then we would describe the spin 1 particle. And this fermion boson star that you see here is for a vector field that has been added. And yeah, you have to be a bit careful in looking at this, because qualitatively it's very, very similar. You also have this kind of stable region of possible configurations. You also have a qualitative behavior, which is very similar to your scalar field case. And this might, on the one hand, might make it possible to distinguish between a scalar field and a vector field, because for the same mass and the same self-interaction strength, you might just get different results in your mass and radius curves, mass and radius region. Or it might also make it more difficult, because then you could change the parameters a little bit and then get results which look very similar for the scalar field case and for the vector field case. And then you might not be able to disentangle both solutions at all. So here's a comparison directly. On the left, you can see the fermion boson star, the combined dark matter neutron star object using a scalar field. And on the right, it is using a vector field. I've used the same masses of the particle and the same self-interaction strength, which is 0 in this case. And here you can really compare them very nicely. So the vector field on the right, it tends to produce larger masses in total, so larger gravitational masses. And also the radius usually tends to be larger as well. And those are the two things where the scalar field configurations and the vector field configurations differ significantly. Right, that the vector field tends to produce higher masses and larger radii. But this also means that, let's say we measure one specific point at 10 kilometers and 1 solar mass. And then we see that both the vector field and the scalar field case do cover this specific measurement. And then we might not be able to tell if it's one or the other at all. So if we continue on this endeavor of finding degeneracies, we can get something like this. So here I played around a little bit with different percentages of the mass being dark matter, and also different masses of the dark matter particle. And here the blue lines are for the scalar field configurations, and the orange lines are for the vector field configurations. And here you can see, especially here with the 60% and 70% dark matter configurations, you can have a vector field or a scalar field, which just has different amounts of dark matter inside of a neutron star. And then you have lines which are almost on top of each other. The same thing is if you look to the bottom left part of the plot. Here in black, I plotted some different nuclear equational state. And then I plotted in green, orange, and blue some other nuclear matter equational state, but this one has dark matter. And then you can see that those lines overlap quite significantly, which might make it very difficult to really disentangle and distinguish nuclear matter effects from dark matter effects. And then the dark matter in itself can also be produce quite similar results depending on which model you actually use. Right? And the bottom line is that we just need more different ways to probe the dark matter. So you really need a holistic approach and kind of multi-messenger approach to try to disentangle all those different effects to then be able to definitively say that you found something or not. So one last part, which is quite interesting, there's some scaling behavior for those of you who are theoretically inclined. On the left, I'm plotting again the scalar, the fermion boson star with the scalar field, but now the scalar field has some mass. And on the right, I'm plotting the vector field configuration, the fermion Proca star, which is called so the fermion boson star with a vector field. But now I choose some different mass. And now if you look at both plots, they look very, very similar. So the small differences here you can see is just the difference in the sample size or the amount of points that were actually computed to produce those two plots. And those look so similar that I thought, hey, maybe this is something more general that can be found here. And it turns out actually that those for the pure boson star configurations, if you only have a scalar field or only have a vector field, then there's some scaling behaviors between the mass, the gravitational mass, and the mass of your bosonic particle. And if you use those two scaling relations for the scalar field case and for the vector field case, you find that if you choose the mass of the vector particle to be roughly 1.6 times larger than the mass of the scalar particle, then you can transform those two into each other, or at least you can find very similar observational properties in the end, so the mass. And more general scaling behaviors also exist for the pure bosonic cases, for the pure scalar field and pure vector field. If you include also non-zero self-interactions. This is something I'm investigating right now, which is quite interesting. because if you are able to scale one solution into the other, it might be good to, you might just numerically, for example, when solving those, one of them, the scalar field case usually is easier to implement. It's cheaper numerically to compute. So you might then just do all your computations with the scalar case and then scale all your parameters back once you're finished, and then get the corresponding values for the vector field. If you're interested in this specific aspect, you can read this paper here that I put here. It's also on the last slide. And in there I talk a bit more in detail what's the deal with those scalar field and vector fields scaling into each other. So with this, we are already finished. Let me just give a short summary. So for those fermion boson stars, the neutron stars admixed with dark matter, we can have core solutions where the dark matter is concentrated inside of the neutron star. We can also have the cloud solutions where the dark matter is dispersed and like roughly just bound to the neutron star itself. And the dark matter can significantly affect the properties of the neutron star, the global properties that will be measured using telescopes or gravitational wave detectors. Then there's some degeneracy between the equation of state, the nuclear matter equation of state, and your scalar field or vector field configurations. And the scalar field and the vector field configurations, they're qualitatively very similar actually to each other. But with a difference that on the quantitative level, the vector fields tend to be larger and more massive compared to scalar fields. With this, I'm already finished. Thank you very much for your attention, and I'm waiting for questions.